Yeah, good afternoon, ladies and gentlemen. It's a great pleasure to be here. I'm very grateful for... Pardon? You don't understand me? Is that okay? Perfect. So, belonging to this first generation of Complas attendance, or what is the name? You know, first Complas meeting, 1987. It's really a long time, also for me. So I would like to acknowledge the work of my co-authors, Professor Manfred Bischoff, the head of the institute, my former PhD student, and is now my boss. And the two other guys here, Christoph Wilking and Martina Madsen, are postdocs. Both left the institute already and are working in the engineering practice. And I have the pleasure to cooperate with these people, and that makes a lot of fun for all the... Excuse me? The microphone is leaving me. Makes a lot of fun for somebody, is in a retired stage. So I'm going to talk about alternative contact formulation. So I was supposed to talk about two kinds. Due to the time limit we have today, I decided just a minute ago to leave off the first part, which is a very minor part, and you can read that part in the book, which will be distributed later on in September, I guess. It comes to the market. And so I will concentrate on the isogeometric analysis later on. So I would like to say that my talk is method-oriented, and it's a little bit keen that I talk in a computational plasticity conference on purely elastic problems. I have to apologize for that. Of course, it can be extended to plasticity and so on. And I just would like to say that I would like to dedicate my lecture to you, Roger. We know each other for a very long time, and I still remember the time when we made some pilgrimage, I guess is the expression, to Swansea, visiting all these nice conferences in Swansea. It was a kind of mecca for us, and that was a time when I have seen you the first time. So it's also a very long time. And we have seen part of this picture already today. It's the couple of the Owens right after Complas 2011 when Roger was elected or was inducted as a foreign member of the U.S. National Academy of Science. So, as I said, I will skip the first part, but I have to say a few words on the basics here, and I would like to apologize that I restricted the mathematical machinery to the essential parts. You don't see a lot of equations here. I just concentrate on some parts of it. So, and these some parts I will explain. I don't explain all the mechanics here, which is well known. I will concentrate here on the virtual work of the contact part in the normal and the tangential direction. And of course now we have to satisfy the Karush-Kuhn-Tucker conditions and so on. We have the normal gap, we have the normal traction, same in the tangential area. We restrict ourselves to Coulomb friction. And in the first part, which I'm not going to talk about, also Lagrange multipliers are used as seen here. And Martina Madsen, in the second part for the IGA, used the penalty. But I'm not concentrating on the Coulomb fraction here. It's an important part, of course, so I neglect that for the time. It's included, of course, but I will primarily talking about this equation here, and in particular of the choice of the Lagrange multiplier. So that means that we are looking at that equation. We have to discretize the integral here, and would like to use either Lagrange finite elements or NURBS functions as seen here for the position vectors and, of course, for the displacement then. And this is the equation I mostly talk about here. How to discretize the Lagrange multiplier in that sense. So we'll talk about the Lagrange parameter basis functions. So this part, as I said, I will skip now, and I move on here to, this is a book, it's coming out soon, so I'll leave it here for you to read, and I come now to the isogeometric analysis. So there is a very nice paper, by the way, by Laura De Laurentiis, Peter Riggers, and Tom Hughes on the isogeometric contact. It's a review paper. I can recommend that, 2014. And of course, everything is described in that paper. The original node to surface concept, which I will not touch today. I will come to this one, point to surface, PTS, where I will use the collocation method, and this is contrasted to the mortar method, where we have to solve this integral in a usual way using quadrature rules and so on. So the main part is this collocation part, and as usual in the IGA, geometry displacements, are discretized by NURBS functions, and now I'm talking about the Lagrange multiplier. The Lagrange multiplier, of course, could also be some kind of NURBS function. As you can see here, it can be quadratic, it can be cubic, and so on. It could be also linear or constant. Later on, you will see some examples where we simply use the constant representation here. Or it could be pointwise. So that is the choice you have. So the well-known mortar method, the integral approach, you have the discretization here. You project that from the slave to the master. You have some numerical integration using Gauss points, for example. And you satisfy an integral non-penetration condition. And what comes out for the Lagrange multiplier are the contact stresses. This has been done in many ways, for the Gauss point to surface or segment concept by these people and others, or in a very similar way for the mortar concept. And in this case, of course, you include this part here in the discretized integral, as you can see here, in the usual fashion. On the other hand, you can come now to the collocation method. And you are talking about a pointwise projection from slave to master. And that is both very interesting for me, because I made my PhD in some kind of shell analysis using collocation. It was in 1972, and at that time we called all these methods the methods of the weighted residuals. This was just one part of it. I was quite satisfied with this, and then I recognized that this method is disappearing. And since a couple of years, it starts again. There's a renaissance of the collocation methods, in particular coming from the IGA community. And that is interesting, and that's why Martina Madsen started to work on that and looked for these contact problems using collocation. It means simply, we dropped that here. This part, the integration is condensing to a pointwise evaluation. That's what we call collocation. And then you have a pointwise non-penetration condition here and that. And you are dealing with contact forces, not with stresses, of course. And Martina Madsen has applied this equation that means the weak form of this contact equation, whereas Laura De Laurentiis and others have used that in a strong form already. So we ask ourselves, Martina Madsen worked on that, is there something in between where we can really exploit also this term in the pointwise approach? And there is something in between, and that's what I would like to talk about. Let's look at that part What does it mean? The points get a certain weight, and the weight can be, depends on some weighting factors, omega here, and so on. So it's a weighted point-to-surface approach. PTS plus, we call it, is a collocation with weights. Again, we still keep this simple, efficient, point-wise non-penetration condition, but we get some contact stresses because we have a certain influence domain around this collocation point, and in this way we come closer to the motor methods. So how to derive these weights? That is not a unique way to get. There are many ways to do that. Here in this case, I only point out to this one here, this integral is just discretized in this way, where you use the shape functions for the slave here, discretize that and sum up, and then from this equation you can solve the weights. For example, it's not the only one you can do that. And then you have to ask yourself, what kind of Lagrange multiplier fields we should use, and of course they can be also discretized in different ways. I mentioned that already. Can be NURBS here in that sense, or we could just take a constant one, piecewise constant. Each collocation part has some part around it, a constant domain. So to sum up here, PTS on one side, point-wise, of course. The evaluation points are the collocation points. They are defined. It cannot be more. You just keep that, NS. And the location of the Lagrange multiplier are the collocation points as well. This one here, is still point-wise, and so far efficient. The collocation points, again, like that one. And now we can decide, constant NURBS type of representation of the Lagrange multiplier. And on the integral method here, the motor methods, we use quadrature points. And you can immediately see that you have a lot of them compared to this one. So the control points in this way are, of course, the location of the discrete Lagrange multipliers. One example, very simple example. It's essentially borrowed from the three-dimensional problem, but analyzed in the two-dimensional way. We have here this slave line, between this yellow one. On the left side, the two methods in this case are very similar, come very close together, the PTS and PTS plus. Botella points are used here in that, and we use the constant Lagrange multiplier field here. The exact solution is, of course, a constant here. And you see both are very similar, not big difference, and the deviation to the exact solution for a relatively coarse mesh is very, very low. Same on the other side. If you have a two Gauss point integration here, you have still also some kinds of deviation here compared to the exact solution. And the 3 Gauss point integration, this is not an error here, it matches the exact solution relatively good. So it looks pretty good, but we have to look at the convergence of these methods. And you see here, due to the relatively low number of evaluation points, or I could say coarse mesh, so to speak, for the collocation points, you have a certain shift here in this direction. 2 Gauss points, that this comes very close to that. 3 Gauss points, even better, and so on. So the rate is identical. That's the numerical experience, of course, identical rate of convergence, and the convergence curve are vertical shifted. So you can ask yourself, why don't you need more, or why do you not use more collocation points? I said you are restricted to the number of values coming from the NURBS discretization. Now going to the same problem, in 3 dimensions. Here we have these 2 other guys here, PTS and PTS plus. Very little computational time for contact. It's completely different already when you have 3 times 3 Gauss points in that direction. And if you get even higher, which is of course not what you usually do, but you see it's a tremendous increase in effort. So that is one of the advantages, you could say, of the collocation method. You know that you have a relatively efficient way because you have very little evaluation points and nevertheless get quite decent results. Here's the Hertzsche contact. The Hertzsche contact quadratic NURBS function for the entire problem, and for the reference solution there is a reference solution used here with a very fine mesh, 250 to 160 elements, and we have then 2 Lagrange multiplier fields chosen, the constant one and the NURBS function with p equal 2. And you see that they all come very close here in this case of PTS plus. For example, the constant one, you know, you have the stepwise representation, and if you go to the quadratic NURBS function, you get a smooth result. Very similar on the right side for the motor type here. You know, you have the stepwise almost identical, and the motor NURBS oriented here, you know, also very similar, except that you have these slight oscillations here. Okay, you think, why not increasing the number of Gauss points? That has been done, and they do not disappear. So that is something which has still to be investigated. So the rotating ironing problem here, 3-dimensional, and you see here the 2 orders, p equal 2, p equal 3, almost identical, and if you zoom in, all 3 methods are very, very similar here. So that is another promise for the PTS problems, you know, approach, PTS plus maybe. And let's go on. Now introducing friction here in this 2-dimensional problem, plane stress problem, and all 3 of them are investigated in this case. And you see here that the left one, the PTS problem, that has some problems. It's a sticking problem because the Coulomb friction coefficient is chosen as big that there is no slip in this surface here, in the slip line, potential slip line. So there's a sticking problem here, and it shows on the left side, on the right side, at the outer edges, it shows that these points slip, which is of course not physical in that case. There's a reason for that, because this point-wise evaluation without this influence domain around it shows that these forces here, the contact forces at the outer surface, they are smaller than these inside, and so they indicate apparently a point slip. So it makes a sense to include this domain around the collocation point. And in this case, you get a better solution here, and the motor solution gives you here almost exactly, or is the exact solution. The color, you know, is different here, but the deviation here in values is very little compared to the purely green part here on that side. So I would like to talk a little bit about shells, only showing some examples that has been introduced in this IGA type of shell formulation, the Kirchhoff-Love formulation used in this case. And again, PTS plus is used, Greville collocation, LM chosen, Lagrange multiplier chosen as constant values. So self-contact has to be included. When you talk about shells, you know, these boundaries might come together. It's a shell surface-oriented contact formulation as mentioned above. Another or 2 examples, again, the Kirchhoff-Love formulation. And then shell to surface, I mentioned that, oriented contact, point to surface, PTS plus is chosen, and these problems are geometrically nonlinear. So the one here, it's just this upper part, the upper ring is pushed down and then slides horizontally here, the edges are put down and then they are put sidewards here. And on the right side, you push the two shells, cylindrical shells, you push them just together, and of course, then you have this contact, and so that works. This was a master thesis of somebody else. So let me just continue here. Few words to dynamics. I will not talk too much about it. It's a classical dynamical problem. We use Newmark, but in this way we have a dissipative modification using the procedure of Kane from 1999, where the acceleration of the problem is split into the internal part and the contact part. And we investigated, or Martina investigated, the impact of a rod. PTS plus is used here. And you see here the results for the energy development, evolution. And you see that here, for the total energy, you have some dissipation, which is not much, but maybe too much. And otherwise it looks pretty good. But on that side, for the total reaction forces here, in that case, you see a reference solution here, so the oscillation around the value 8. Please remember that, 8. But in that case, with this modification, we have a very large oscillation here, 45% deviation from the reference solution. So there has to be done something else, and this something else is that you have to remove the mass on the contact surface, the potential contact surface, from the boundary. This is unphysical here and that point, and there have been proposed different schemes, which I will not explain in detail here, to just remove the mass to the interior part. It affects only the first part of this structure here. So this blue shape function is replaced by the green ones, so it's a relatively elegant and easy concept. So now again, this impact of this bar here, and you see now the energy evolution looks much better. And I mentioned this value of 8. The reference solution is given in gray, and the other two, depending on the two mass distribution concept, are similar, very similar. They are not exactly the same, of course, but they are very similar. So now I show two other examples. Just the same thing has been investigated for this colliding two disks here, and then looking again at that scheme. Again, PTS plus is used here, Greville collocation. And you see here, if you look close enough, the energy in time, both come very, very close, and the same holds also for the sum of contact forces. Apparently, it's not so important what kind of distribution you are doing, but you have to do it. And then the other example, a ring. It's a two-dimensional problem, of course, and the ring is going and bouncing to the left and to the right, rigid part here. And again, the same model is used, and let's just go on. And you see here that the energy, you have these two, occasionally the ring, hits the both parts, and that's why you have these oscillation and you have the special points here. And again, you see if you zoom in, there is a slight deviation between the two methods of mass allocation here. So that looks relatively promising. I was not talking about this dual motor method. I would have talked about the stress recovery in that can for the dual motor method, but I did not do that. You can read it if you like, and I have not shown other things here. So I concentrated on this part here. We think that the collocation point-to-segment or surface and point-to-segment weighted plus here in that it is a promising alternative to integrative mortar. At that point, at the final end of Martina Madsen's dissertation, I had a discussion with her, I said, come on, if you compare both ones, the collocation method is just another way of integrating. On the other side, Gauss points are in a way also collocation points. And there is some very strong similarity in my opinion. So one can, of course, exploit the features of the point-oriented schemes for discontinuities like kinks. And what I have done in my dissertation many, many years ago, I have used the so-called, as people at that time said, overdetermined least collocation, or the overdetermined least square collocation. That is, you use more points, you have more equations as unknowns, and then you make a least square fit, and that's, in my opinion, a better solution, and maybe we should try that also. So thank you very much. I hope I almost in time. So thank you very much.
Yes, thank you very much, Eckhard.